The topic is single source shortest path problem. In this video, I'll show how Bellman-Ford algorithm works and also the drawback of Bellman-Ford algorithm. The problem is, in a directed weighted graph, we have to select one of the vertices as source vertex and find out the shortest path to all other vertices. Let us say if I select vertex 1 as starting vertex, then I have to find out the shortest path to all of them. Now for doing this, already we have Dijkstra algorithm that will solve the shortest path problem. But Dijkstra algorithm will not work if there are negative edges. It will not work properly. It may give correct result, it may not give correct result. So we cannot use Dijkstra algorithm here and confirm that it is giving correct answer. So we want an algorithm which confirms that the answers are correct. So that algorithm is Bellman-Ford and it follows dynamic programming strategy. So dynamic programming strategy says that you try out all possible solutions and pick up the best solution. So here we want to try out all possible solutions and pick up the best solution. How we will try all of them? So this algorithm says that you go on relaxing all the edges. How many times? All edges you repeatedly relax them for n-1 time. What is n here? N is the number of vertices. Number of vertices are 7. So I should relax them for 7 minus 1. What is the idea here? If from the source vertex, if the longest distance may be of all the edges, then total how many edges may be there? So from 1 to 7, there can be maximum 6 edges. So if you are going on relaxing the edges, we may get a longest path also that is of 6 edges, right? So it will cover all possible paths if you relax all of them for 6 times. So what is relaxation? If I take any two vertices, let us say 2 and 5, and I know some distance of this vertex, the path to this vertex and the path to this vertex also, then I should see that if the path of this one plus this is less than this one, if so, I will change this one. So I will call them as U and V and I will write down what does relaxation means. Then once I start using it, I can explain you how it works. So relaxation means what? Between a pair of vertices U comma V, if there is an edge, then check if the distance of U plus cost of an edge U comma V is less than distance of V. If so, then change the distance of vertex V to distance of U plus cost of an edge U comma V. What is that? I will explain you while solving this. Now let us follow the algorithm. What the algorithm says, you prepare the list of all edges. Prepare a list. So which edge I should select first? You select any edge. First you select this one, then this one, or this one, or this one. You select anything, but make sure that all edges are selected. So I'll select them vertex by vertex. So I'll write down the list of edges here. There are total 10 edges. I have taken all 10 edges here, list of edges. Now I have to relax all these edges for 6 times. Now let us start the procedure. For that, initially I have to mark the distances of all these vertices. So this vertex, let it be 0, and for all other vertices, mark the distance as infinity. Mark it as infinity. All are infinity. Now start relaxing the edges. Now I will show you how that relaxation procedure works. First edge 1, 2, 1 to 2. What is the distance of this one? 0. What is the distance of this? Infinity. 0 plus 6 is less than infinity. 0 plus 6 is less than infinity. So change this infinity to 0 plus 6. So make it as 6. The next 1, 3. 0 and this is infinity. So 0 plus 5 is less than infinity. So change this to 5. 0 plus 5 less than infinity. So change it to 5. So first 3 edges completed. Now 2, 5. 2, 5. This is 6 minus 1. This is infinity. So this is 5. 6 minus 1 is 5. This is already changed. You see. 3, 2. So 3 to 2. So this is 5 minus 2 is a 3. So change it to 3. Then 3 to 5. So this is 5 plus 1 is a 6 and it is 5. So that is smaller. Don't modify that one. 4 comma 3. 5 minus 2 is a 3. So this becomes 3. Then 4 comma 6. 5 minus 1. This is 4. This is infinity. So change it to 4. Then 5 comma 7. So 5 plus 3 is 8. This is infinity. So change it to 8. 6 comma 7. 4 plus 3 is 7. This is less. So change. So most of the changes we have seen first time only. Let us continue. Second time. 1 comma 2. So 0 plus 6. 6 and 3. So this is greater than that one. So don't change that one. 1 comma 3. 0 plus 5. 5. That is 3. Don't change that one. 1 comma 4. 0 plus 5. This is 5 only. No change. Then 2 to 5. 2 to 5. So 3 minus 1. 2. This is 2. That is changing again. So 3 to 2. So 3 is how much? 3. 3 minus 2 is 1. So this will change. 1. Then 4 comma 3. 4 comma 3. 5 minus 2. This is 3. This is perfect. 4 comma 6. 5 minus 1 is 4. Perfect. 5 comma 7. 5 is how much? 2. And 2 plus 3 5. This is 7. So change it to 5. Then 6 comma 7. 4 plus 3 is 7. And it is 5. No change. Let it be as it is. I have completed 2 times. 4 more times I have to do. 1 comma 2, this will not change. 1 comma 3, this will not change. 1 comma 4 also will not change. Then 2 comma 5. 1 minus 1. This becomes 0. This becomes 0. Right? Then 3 comma 2. So 3 is how much? 3. 3 minus 2. 3 minus 2 is 1. Already 1. Now no more changes. Then 3 to 5. So this is 3 plus 1. 4. Already it is 0. That is better. 4 to 3. 4 to 3 is how much? 5 minus 2. That is 3. No change. 4 to 6. 4. No change. 5 to 7. 5 is how much? 0. 0 plus 3. 3. This becomes 3. Then 6 to 7. 4 plus 3. 7. That 3 is better. Right? So I am updating there only. So 3 times I have completed. 3 more times I have to do. 1 to 2 will not change. 1 to 3 will not change. 1 to 4 will not change. 2 to 5. 2 is how much? 1. 1 minus 1, 0. That is not changing. Then 3 to 2. So 3 to 2, 3 is how much? 3 minus 2, 1. 1, it's already 1. Then 3 to 5. So this 3 plus 1, 4. That is better, 0. 4 to 3 will not change. 4 to 6 will not change. Then 5 to 7. 0 plus 3, 3 only. 6 to 7, no change. Now this has stopped changing. So what are the results I got? Vertex 1 is 0, vertex 2 is 1, vertex 3 is 3, vertex 4 distance is 5, vertex 5 distance is 0, vertex 6 distance is 4, vertex 7 distance is 3. These are the distances I got. If I continue for 2 more times also, I'll get the same result. So finally, these are the shortest paths. You can observe that. So as I am doing it manually, I have stopped. But when you write in any algorithm for doing the same thing, it will continue for n-1 time. And some graphs may get the shortest path in just 1 time relaxation only. And some graph may relax completely, get the shortest path in the last relaxation. So in this graph, we find that after the 3rd one onwards, there are no more changes. I have taken the shortest paths. So this is how Bellman-Ford algorithm works. Let us look at the time complexity of Bellman-Ford. What it is doing, relaxing all edges. How many edges are there? E edges are there. How many times it is relaxing? V minus 1 time. So this is order of V into E. So if we say V and E are nn, so this will be n square. So it depends on the number of edges. If this is a complete graph, then how many edges will be there in a complete graph? A complete graph means there is an edge between every pair of vertex. So total how many edges will be there? N into n-1 by 2 edges will be there. So if these many edges are there, then the time will be n into n-1 by 2 into number of vertices minus 1, n-1. So if you simplify this one, this will be order of n cube. So in case of complete graph, Bellman-Ford algorithm may take even n cube time, right? Otherwise, minimum time we say it takes n square, and at most it may take n cube time. That is if the graph is complete graph. Now we'll take a small example and solve it, and also I will show you drawback of Bellman-Ford. A small example, I will take the list of edges. First of all, I will take the edges starting from here. First I will take 3, 2, then I will take 4, 3, then 1 to 4, then 1 to 2. See, just to make you feel how the relaxation are done, I have taken the vertices in reverse. I should have started from vertex 1. Now let's solve this. My source vertex is 0 and mark all of them as infinity. Mark all of them as infinity. How many times I should relax? There are 4 vertices, so I should relax that for 4 minus 1, that is 3 times. So let us relax all the edges one by one. First 3, 2, infinity minus 10 is infinity only, so that is no change, it is already infinity. 4, 3, infinity plus 3 is infinity only, and this is already infinity. Then 1, 4, 0 plus 5, 5 is less than infinity, so change it to 5. Then 1, 2, 0 plus 4, 4 is less than infinity, change it to 4. One time I already have relaxed. Second time, 3, 2, infinity minus 10 is 4, that is better. 4, 3, 5 plus 3 is 8, this is better than infinity, so make it infinity. 1 to 4, 0 plus 5, 5 only. 1 to 2, 0 plus 4, 4 only. 2 times I have completed, one more time I have to complete. Let us check. 3 to 2, 8 minus 10 is minus 2. Minus 2 is smaller than 4. Now you can see that I got the correct answer for vertex 2 now. Then 4 to 3, 5 plus 3, 8 only. 1 to 4, 0 plus 5, 5 only. 1 to 2, 0 plus 4. And that is not greater, not less than minus 2. So minus 2 is better. Let it be as it is. So I have relaxed them for 3 times and I got the shortest paths. So what are the shortest path? Vertex 1 is 0, vertex 2 is minus 2, and vertex 3 is 8, vertex 4 is 5. These are the shortest path from starting vertex as 2. So Bellman-Ford has got the answer even when there are negative edges. So this is the answer. If I relax this for one more time and see, let us what happens. 3, 2, 8 minus 10 minus 2 only. 4, 3, 5 plus 3, 8 only. 1 to 4 and 1 to 2 all are same. So if I relax one more time extra also, there is no change. That means the answers are perfect. Now let us see the drawback of Bellman-Ford. I will take the same graph only, but a small change. The same graph, I will add one more edge, that is 2 to 4, and I'll make it as 5. So this is 2 to 4. Now let us relax them. I have to relax them for 3 times. So quickly I will do it because already till here I was doing it. Let us do. So 0, infinity, infinity, and infinity. 3 to 2, infinity only. 4 to 3, infinity only. 1 to 4, 0 plus 5, this is 5. 1 to 2 is 0 plus 4, this is 4. Now 2 to 4, 4 plus 5, 9, this 5 is better. No need of changing. One time over. Now 3 to 2, infinity minus 10, that is infinities. So 4 is better. 4, 3, 5 plus 3, this is 8. Then 1 to 4 is same thing only. 1 to 2 is same thing only. Then 2 to 4, 4 plus 5 is 9, and this is 5, that is better. 2 times completed. The third time, 3 to 2, 8 minus 10, minus 2. Then 4 to 3, 5 plus 3 is 8, 8 is there. 1 to 4 is 5 only. 1 to 2, 0 plus 4, so minus 2 is better. Then 2 to 4, minus 2, and 5 is 3. This 4 is changing. Right? So this was the third time I have done and I got this answer. Let me try for one more time. Already n minus 1 time I have done. But let me try one more time and check. 3, 2, 8 minus 10 is minus 2 only. Yes. 4, 3, 3 plus 3, 6. Oh, this is changing. 1 to 4 will remain same, 1 to 2 also remain minus 2 only, and 2 to 4 minus 2 to 5 is 3 only. Minus 2 plus 5 is 3 only. So one more vertex has just now relaxed. That should not happen. After completing for n minus 1 time, I should get the answer. If I repeat it for one more time, if I relax all the edges, there should not be any change at all. If I do one more time, again something will change. See, 3 comma 2, 6 minus 10 minus 4. So that's what there is a problem. So why we got this problem? Bellman Ford is unable to solve this one. After performing for n minus 1 time also, I am not getting the correct answer. Still they are getting relaxed. So even if I do it without Bellman Ford, directly if I try to do, I cannot solve it. Reason is there is a cycle of edges, that is 2 and 4 and 3. So this is forming a cycle. This is minus 10 and 3 and 5. So if I add this, 5 plus 3, 8, minus 10 is minus 2. The total weight of a cycle is negative. So in this way, I'll be going on getting the path reduced every time. So there is no end of this one. So I cannot decide or freeze the answer. So if there is a negative weight cycle, then graph cannot be solved. Right? So Bellman Ford fails to solve the graph if there is a negative weight cycle. Total weight of a cycle is negative. If it is positive, it will work. So if weight is negative, it will not work. That's all. Then, but a Bellman Ford algorithm can detect if there is a negative weight cycle or not, because after performing for n minus 1 times, we can relax one more time and check if the vertices are getting relaxed. If any of the vertex is getting changed, then it means there is a negative weight cycle. So that's all about dynamic programming Bellman Ford algorithm.